Welcome to CPE 350, Chapter 6.2, in which we solve the heat equation for a semi-infinite geometry. So from our last lecture, we had defined the governing differential equation in its dimensionless form for the case of transient heat conduction in a rod, where the rod was semi-infinite relative to the rate at which conduction is happening. And this is our equation. So we just need to solve this second order ordinary differential equation. And the fastest way is to make a substitution of u for the first derivative. And so if we substitute that into our governing equation, it collapses to a first order separable differential equation. And we pull the u's over to the left-hand side and all the etas over to the right-hand side. And integrating, we get an expression for the natural log of u in terms of eta squared and a constant of integration. And at this point, the 2's cancel top and bottom, and we're just left with a negative eta squared, which may not seem particularly relevant, but actually it will help us in the rest of the solution of the problem. And that factor of 2 is actually why we added a factor of 4 into our expression for eta. If you'll remember that eta is x over this strange factor of 4 times alpha t. So this is why we added that 4, so that we could cancel out these 2's in this step. Okay, continuing on with our problem, we'll solve for u, and we're just basically lumping our constants of integration to make the expression as simple as possible. And then we replace u back for d theta d eta. And again, we can separate this and integrate it. And when we do that, we get an expression for theta. And it's really tempting to look at this and think that you can integrate that exponential of negative eta squared, but there's no analytical solution for that integral. So you can't actually integrate it. And it's just one of those little surprises. But what we will do is find a mathematical function that helps us work with that non-analytical integral so that we can calculate numerical values easily. But in the meantime, this is our solution to the heat transfer equation. And in the next step, we'll solve for the constants.